Let's practice working with the multiplication principle together. All right, so for number one, we're going to go ahead and flip a coin 3 times. Again, the assumption is that these coins are going to be fair. So if you flip a coin, you have 2 options. Essentially, we have heads and tails. And then if you go ahead and flip that coin again, if after it's heads, it could be heads and tails, right? Those are 2 possibilities. And then same thing after it's tails, it could be heads or tails for that second flip. And then for the third flip, after that, it could be heads or tails. Same thing for all of these. So go ahead and just draw these out. Make sure you just try to spread out the tree branches a little bit here. Sometimes they can get a little cluttered, so it's always good to try to spread them out so that you can hopefully plan ahead for that. All right, so this would be a nice tree diagram for this first one of flipping a coin 3 times. So in terms of the number of unique outcomes, you can see there are 1, 2, 3, and 4, and 5, and 6, and 7, and 8. So there are really 2 choices in the beginning, and then 2 choices, and then 2 choices. So altogether there are 8 outcomes. All right, for number 2, it says, what if you're going to be choosing an outfit that you have 2 shirts, and then you have 3 pairs of pants, and then 2 pairs of shoes. So all right, so it's up to you if you want to go ahead and create like one big tree. I'm going to actually split into 2 different ones, and you can use this as a strategy as well. But I'm going to call this shirt number 1, and then I'm going to separate this, or say that we have 3 choices here for the pants. I'm just going to call the pants P1, P2, and P3. And then if we go to the shoes next, I know it's a little confusing if I use S again, but hopefully it's clear enough to you that I'm using these S1s and S2 for the shoes here. So that's going to be the shoes. Shoes 1, shoes 2, shoes 1, shoe 2. So in terms of the possibilities here with the shirt number 1, these would be all the combinations here. All right. What about for shirt number 2? Basically just replicate the same thing here. I know it could be a little tedious to do these, but they're not too bad, hopefully, in terms of complexity. So here are the 3 pants options here. And then for the shoes, of course, we have 2 options for each of these outfits. Okay, so probably spreading it out is probably the most tricky thing to kind of do here. So what are all the possibilities here? So there's 1, there's 2, there's 3, there's 4, there's 5, and there's 6. If there's 6 over here, and then there's 6 over here as well, that's a total of 12. And to back this up, you can use that multiplication principle and say, well, there were 2 possibilities for the shirts, also 3 choices for the pants, and then 2 choices for the shoes. So multiplying these together, we would get 12 outfits here, right? So that's another way you could go about it, and that kind of verifies what we see in the tree diagram as well. All right, cool. Let's go ahead and check out questions 3 and 4. Here we're going to use the multiplication principle. We don't have to draw any tree diagrams here to determine the number of possible combinations using 1 of each choice from the options listed at the local ice cream store. So let's see, we're going to be choosing something from each of these. So we have to choose a size, a topping, sprinkles, and a container. So again, the assumption is always that we're going to be choosing 1 from each of these if it's not specified otherwise. So it says an order with no topping. So here are the specifications with no sprinkles. Interesting. So no topping. So we do have to choose a size, right? So how many possibilities are there for the size? Well, for the sizes, there's going to be 3 sizes we could choose from. It says no topping, so we're not going to be choosing any from here, so don't worry about this here. It says no sprinkles, so don't choose anything from here as well. But we do have to choose a container size, so it looks like there's 4 different choices here. So this would be equal to 12 possibilities. Again, if you think about it, you could do a small with each of these options, then you could do a medium with each of these options, then you could do a large with each of these options. So there would be 3 by 4 or 12 possibilities. All right, number 4, it specifies an order that's going to be in a cone, but there's going to be no sprinkles here. So we still have to choose a size here. So we would have 3 choices for there. We are going to choose a topping. Again, the assumption was choosing 1 topping here. So we have 4 choices to choose from. So we have 4. And then it says without sprinkles, so don't worry about sprinkles in this particular one. And then we do have to choose, it says it's going to be in a cone. So how many options are there for cones? Well, there's really 3 options for the cones here. And so you have to kind of just read carefully and know what they're asking. And so in this case, 3 by 4 is 12 times 3. So there's going to be 36 possibilities or combinations. Now, if you're wondering what the total possible combinations there would be if you did choose one from all of these and you had to choose a size, a topping, sprinkles, and container, there would be 3 over here, there would be 4 choices here, there'd be 2 choices here, and then there'd be 4 choices here. So you'd go ahead and multiply all these together. I believe that would be 96 total like unique combinations here. And again, that would be the assumption if you were just being told and being asked to find all the possibilities if you chose exactly one from all these. But you can see here in questions 3 and 4, they were just being a little bit more specific and trying to see if you could see the difference there. And so hopefully you were thinking, okay, you could multiply all this together to get all the possibilities. But for 3 and 4, we were thinking about some more specifics there. All right, so there's 3 and 4. Let's check out a few more to practice. All right, in questions 5 and 6, let's go ahead and apply our understanding of the multiplication principle to answer the following questions. Let's make sure we show our work as well. So for number 5, we want to unlock your friend's iPhone, but it has a 6-digit passcode that consists of only numbers. The question here is going to be, what's the probability that you guess correctly on the first try without knowing any additional information? Okay, well, there are 6 digits here, so generally it's a good idea to write out our spots for our 6 digits, 1, 2, 3, 4, 5, and 6. And then let's go ahead and multiply all the choices we have for each one, right? So let's see, if you don't know anything about this, we have to assume that everything is going to be random. And we can say that you have 10 choices. Keep in mind that 0 through 9 are all the digits, or single digits, and that's 10 numbers. So there are really 10 choices. You could have the same number each time. So there's nothing, kind of telling us that we can't choose any number specifically here in this first part, right? So in terms of the number of possible passcodes here, this would just be really equal to what, 10 to the 6th power. So that would be, I think, just 1,000,000, right? So that's to be 1,000,000 combinations. But it says, what's the probability that you guess correctly? So the probability of being correct, remember that capital P, and then this is the event that's happening. So the probability of being correct here on your first try, if you don't know any additional information, is going to be 1 in 1,000,000. All right, so that's going to be that first part, but let's kind of start over in part B. It says, what's the probability that you can guess correctly if you had some additional information here? So they're being told, or you're being told, that there are no repeat digits. So here are the 6 spots, 1, 2, 3, 4, 5, and 6. So same kind of format here. What if you're told there's no repeat digits? Well, when you're first choosing the first number, right, you really have 10 choices, but after you choose a number, you can't choose it again. So there's really only 9 choices, then 8 choices, 7 choices, 6 choices, then 5 choices. So if there's no repeat, then you have less and less choices as you go. Now, if you go ahead and multiply this out, you might need to use a calculator for this to speed up the process. This is going to be 151. 200. So what's the probability of being correct here? I hope it makes sense that you have a much higher chance of being correct because there's less possibilities. It's going to be 1 in 151,200. So your odds are significantly better, but still pretty unlikely that you would get it correct here. All right, in part C, it says, what's the probability that you guess correctly if your friend tells you that there are only even numbers? Again, the assumption is we are starting over from scratch here, but we have different parameters. So 1, 2, 3, 4, 5, and 6. If it specifies that you're kind of going off of the other parts, then sure, you would want to consider it. But I think it's safe to assume here that these are just kind of new scenarios each time, right? So if we are choosing only even numbers, or you know there's only even numbers, it doesn't say anything about repeating or not repeating. So the assumption is that you can repeat numbers. So how many even numbers are there between 0 and 9? There's 0, 2, 4, 6, and 8. So there's 5 choices. So you really have 5 choices for the first one. You still have 5 choices, you still have 5 choices, you still have 5 choices, 5 choices, and 5 choices. So you really don't have to worry about not repeating any numbers. It doesn't say anything about that. So you can choose the same even number over and over if you want as well. So this is going to be 5 to the 6th power. So go ahead and multiply that out. And if you multiply that out, you should get something like 15,625. That's how many possible combinations are if you only use even numbers for this passcode. Okay. Now, what's the probability of being correct here? Well, the probability of being correct, hopefully it makes sense. It's significantly better odds for you at this point because there's a lot less choices, right? So it's going to be 1 in 15,625. If you only get one guess, this would be the probability that you would be correct, assuming you knew no other information besides what you're told in the problem. Okay. All right, let's check out the last problem. It's got a few parts here though. So in number 6, it says a multiple choice test contains 4 answer choices, A, B, C, and D for each question. You guess randomly on 2 questions on the test. So for part A, it says just make a tree diagram of the possible answers for the last 2 questions. All right, so you could make one bigger tree diagram here, but I'm going to go ahead personally and separate this though into 4 smaller trees. So 4 options after you choose A. So if you choose A for the first question and you guessed, for the second question, you could still choose A, B, C, or D for the next question, right? Hopefully this makes sense. This is going to be the same for each of these. So what if you randomly guessed B on the first question? Well, you still could choose A, B, C, or D for the second question. If you chose C as your guess for the first question, you could still choose A, B, C, or D for the second question. And then if you chose D for the first question, you could still choose A, B, C, or D. So again, you could have made one big tree, but I kind of just made 4 smaller trees here. These being your choice for the first question, and then these being the choices that you had for the second question. So a combination you could have is AA, AB, AC, AD, or BA, BB, BC, BD, CA, CB, CC, or CD, or DA, DB, DC, or DD. So in total, how many possibilities are there? Well, you had 4 choices for the first question and you had 4 choices for the second question. You have 16 possibilities in total. All right, so if you are just guessing that you would be correct for both of these, well, the probability of being correct on both questions, it's not very good, is going to be 1 out of 16. All right, for part C, this is the last part of this question. It says, suppose the answer to both questions is A. Use the tree diagram to count how many outcomes there are in which you would answer at least one of the 2 questions correctly. Then it says, what is the probability that you would answer at least one question correctly? So let's go ahead and see. We're going to write this as the probability of getting at least one correct. So I'm going to say greater than or equal to 1 correct. And what would that be equal to? Well, so it's basically saying 1 correct or 2 correct, right? So let's look at our tree diagram here. Both of them happen to be A. So this would be 1. This is one possibility. That's 2 A's, but that's fine. 2, 3, or 4. So you have 4 possibilities so far. This is 5 because there's 1 A here. That's 6, and then there are 7. So you can see there's a total of 7 possibilities here. 6 of them have just 1 A, so 1 being correct. There's one of them where both of them are correct if you happen to choose A and A. So notice how it says at least 1, so it's 1 or more. So there's 7 possible outcomes that you could have had where you got at least one of those correct. So it's going to be 7 out of how many in total? Well, out of the total, we knew there were 16 possibilities, so it would be 7/16 in terms of the probability. And then it did say or ask the question of how many outcomes would there be. I forgot to write that first, but there would be 7 outcomes where you have at least 1 correct. But in terms of the probability, it would be 7 out of 16. And you could write that as a decimal or a percent as well if you wanted to know those in those forms as well. All right, cool. So there you have a few different practice problems where practice using some tree diagrams as well as the multiplication principle. If you found the video helpful, please consider giving it a thumbs up and sharing with a classmate or friend who might also find it helpful. And as always, keep up the great work that you're already doing.